Alright, what's up everybody? So for today in our video series going from a noob to a veteran ASM coder, we are on episode 11. So this is going to be the first episode covering the tier level of intermediate threads. So we've already done all the newbie threads, we've done the beginner threads where you actually learn how to become for your first time ever, a real code creator, learning assembly from scratch, and some really basic assembly stuff like register safety and basic debugging and analysis of ASM codes. So now we are at the intermediate level. So you're probably getting to the point now to where you might have to optimize your codes because they're actually getting complex enough where it's required. So at first, in the previous episodes, I talked about don't worry about optimization until you skill gets increased enough over time where it actually matters. Well, we're actually at that point now. So this little thread, ASM tips and tricks, will just give you some little pointers to help optimize your your ASM sources. So this first one, part 1, what do we got here? Alright, let me get a sip of water. So a beginner ASM coder might write something like this in their source. They'll write the upper bits of an address and then the lower 16 bits, and they want to load a word from it. I mean, it works. I mean, it's fine, but it's not completely optimized. Remember we talked about in loading and storing instructions, the 16-bit signed value here back in the assembly tutorial. Alright, you add this value, which we call the offset, and you add it to the value in the source register, and you get the effective address, aka the specific address for, in this case, we want to load from. So with the 0, when we're not even using this, so we're like leaving a portion of the instruction unused that we could use to our benefit to save us the amount of source to write. So what we can do is, instead of doing that, instead of writing the lower bit amount, we can use the lower bit amount as the offset. So you see what happens here? Add R12 value, which is this, because at this point, remember, R12 is that, right? So you add 1650, it's the same as doing this or immediate instruction. So now this is still loading it from the same spot, but you don't need this middle instruction up here. Alright? Easy to do. Now, you're probably telling me, well, Vega, that value is 16-bit sign. What if it's greater than... What do we do? Okay, simple trick to do this. If your offset amount that you want to use is going to exceed the 16-bit sign limit, so first, you're going to write out your load immediate instruction, but add 1 to upper 16-bit value. So whatever value you're gonna set for the upper 16 bits, you just add 1 to it. Now the next instruction you do is you still have your load word instruction. Now let's say the address we're loading from, just for this example, was this, because obviously 9CCC is greater than 7FFF. So this was, we just added 1 to this. 8,000 plus 1 is 8,001. Now, if you plug in your offset value or your lower bits, this isn't going to work because of the 16-bit sign limit rule. All you do is what we call sign extension, meaning you just add 4 F's before it. Obviously, you can only do this if the offset value is greater than 7FFF. So what this actually does is, this increases this amount at the exact right amount to where if you change your offset value to a negative number, it still loads it from the same spot in memory. Just sign extend. So that's all you need to do if your offset value is greater than 7FFF. Okay, simple enough. Go to the next example. This one's pretty self-explanatory, but let's say you have these two instructions at the end of your source. or somewhere in your source where once you use R12 you no longer need it. Why would you use R11? Especially if you're getting to the point where you need to start using other registers other than the ones that are part of a default instruction. As before in the register safety episode, you only have so many registers you can work with before you do what's called the push/pop the stack method, which greatly increases the length of your code. So if you don't need register 12 anymore after this, you can load it right back into register 12. Kind of like the concept we talk about in the assembly tutorial episode. Like for an add instruction, you can use, if you want to, if the code you're working on, what you want allows it, you can use the source register for also the destination register. Source register, destination register. Obviously, remember this takes R12's old value and changes it to the new one, so keep that in mind if you're doing this. But this can help shorten your source. What we call it loading a register into a register. Let me get a sip of water. Okay, there we go. Okay, I've seen some people do this before. This one's pretty common sense, but just in case. You can see we have a redundant instruction, but they're using two different registers. This is not needed because, as you can see in this source, register 12 is never being modified. So we can still use it for a later instruction, for the secondary load instruction. Delete that, change this to 12. Excuse me. So that right there will help shorten one instruction on your source. Alright, let's go to the next one. This one's really important. So if you're the type of coder, beginner coder, that likes to use read breakpoints a lot, obviously you'll run into a lot of loading instructions like this. So the noob, the beginner ASM coder, might write something like this. Do you see the issue here? Why would we take the value that we set in the register, store it to dynamic memory, and then load it back into the register again? That's redundant. So for most codes, simple ASM codes that you make with a read breakpoint, where you have a default instruction, a default loading instruction, you can just do this instead of up above. Now some codes, depending on the code, depending on the static memory address that you are manipulating, you may have to write your new modified value back into dynamic memory, which all you want to do is this. There is still no need to have the default loading instruction. Alright, simple enough. So there you go. We'll go into the next portion. There's a thing for optimizing branch routes. The one thing I want to point out, because branch routes can vary so much, obviously, depending on what the code is doing, what values you're comparing, how many times or how many items you want to compare. But if you have a source and it has like a branch if equal or a branch if not equal instruction, and then right below it is an unconditional branch, take a second look at it. Chances are it's not optimized. I show a basic example under part 5 of this thread, unoptimized version, and then we optimize it. Simple enough. Alright, portion 6 of this thread. So remember I told you guys in the ASM register safety episode that sometimes you can just push and pop the stack if you don't want to worry about what free registers you can use. All this covers is that, keep in mind, it just makes the code that much longer. So it just recommends that you go ahead and look beyond your code address, what we talked about also in the register safety area. It's just all portion 6s. If you want to cut down your code as much as possible, avoid push/popping the stack method. That's all it talks about. Okay, so this is another important one right here. Let's say you have this. Certain instructions, like the common add instruction right here, they have a special feature or an option. It's called record. And what is the record feature? The record feature equals this. Or in hex, you can put that. Doesn't matter. You get a free use of a comparison of the destination register to the value of 0. So what does a record feature or option look like on an instruction that's capable of having it? And keep in mind, there's so many instructions for PowerPC assembly. There's no way I can list, I mean I could, but it'd be a nuisance, which instructions have the record feature and which ones don't. It varies quite a bit, but the add instruction does. So to make the record feature, you just add a dot. No, it's not a typo. The dot's meant to be like that for the record feature. And then you can do that. Keep in mind that the record feature is comparing to 0. So if you have like comparing a value or comparing a register to like a value of 10 underneath the add instruction, it will not work because the shortcut is for comparing to 0 only. So a little record shortcut for you. Make things a little bit, make your code a little bit shorter. And I know I haven't talked about really floating point values a lot. We just briefly covered them about register safety and whatnot. But this would accomplish the fact that I run into some beginner coders that do work with floating points. They want to set a floating point register to the value of 0. Let's say you want floating point register 1 to equal 0. You take whatever register it is, and you do what's called a floating point subtraction instruction, and you just put the same register all 3 times for the instruction format. So, excuse me, if you want F1 to equal 0, it would be F sub F1, F1, F1. So that's how you would set a floating point register to the value of 0. And I think that's pretty much it, guys. That will cover some basic tips and tricks. I think the biggest ones here to take away is really like a register and a register, the offset value trick, especially for the sign limit, how to bypass essentially that sign limit, and just really a good example I provided in the thread of optimizing branch routes. That's all there really is. So in the next episode, it's going to be a pretty big leap in skill level, if you will. So you might be stuck in this next one for a while, but it's going to be called using the exception vector area. That'll be for the next episode. Alright guys, thanks for watching.